Hey everybody, welcome to the Benzoin Condensation lab. Here's the outline for the video. I'll be going over the reaction and talking about the procedure and some of the conditions for this reaction. Then I'll show the experiment in the lab. And at the end, I'll take a look at the NMR just because there are some things on there that we haven't seen before, so I wanted to go over it really quick. Here's the reaction that we'll be doing. We'll be taking two benzaldehyde molecules and reacting them with each other to form the benzoin compound. And we'll be using thiamine as the catalyst as it will stabilize the intermediates throughout the reaction. Here's a look at the mechanism. Thiamine initiates the reaction and creates a tetrahedral intermediate that interacts with water. Then sodium hydroxide pulls off a proton and creates a nucleophilic carboanion stabilized by the thiamine that can then attack another benzaldehyde molecule. Then, as that intermediate interacts with hydroxide and water, the alcohol group is formed, and as the tetrahedral intermediate collapses, the ketone group is formed, and thiamine is reproduced, and the benzoin product is formed. Notice that when the carboanion attacks the benzaldehyde molecule, it is not stereospecific, so when we look at the orientation of the alcohol group and the stereocenter formed, we're going to see a racemic mixture of the R and S enantiomers. During the reaction, we'll want to be careful to control the heat and basic conditions because if it gets too hot or too basic, thiamine can actually start to decompose. Also, if we add too much base, benzaldehyde will just start to react with itself like we saw in the Cannizzaro reaction. So we'll add the base dropwise slowly until the solution turns yellow. And that's because thiamine hydrochloride is a salt and it's colorless, but as it interacts with sodium hydroxide, it turns a bright yellow color, and so we'll just add the base up until that point. We'll also do the reaction in a water bath and measure the temperature with a thermometer. So the apparatus will look like this, and we'll keep the temperature between 60 and 65 degrees Celsius. We'll let that reaction go for about 90 minutes, but about an hour in, we'll test that the product is forming using TLC. And what we're looking for is a big enough spot on the TLC plate for the benzoin product, not the majority of it just being benzaldehyde. So we'll make two spots on the TLC plate, one from the product reaction mixture from the conical vial, and the other from a benzoin standard, just to make sure that we are forming benzoin and not some other compound. Once the TLC plate is developed, it could look something like this, where the bottom spot that didn't really move at all would be for thiamine, then the middle spot would be for benzoin because it matches with the standard, and then the top spot would be for benzaldehyde since it's less polar than benzoin. If the TLC plate does end up looking like this, where there is more benzaldehyde reagent than benzoin product forming, then we can simply add some more thiamine and let the reaction continue. Once the 90 minutes have passed, we'll let the product crystallize out of the reaction mixture and gather those crystals through vacuum filtration. At that point, we'll rinse that solid with cold 50% ethanol, which is to help remove any of the benzaldehyde that would have been left over from the reaction. Then we'll recrystallize the product using 95% ethanol and characterize that product by taking a melting point and running an IR spec. Alright, I'm going to start by weighing out 37 milligrams of the thiamine hydrochloride salt and add that to a 5 milliliter conical vial with a spin vane. Then I'll add 110 microliters of water to start dissolving the thiamine hydrochloride, and I'll mix it with the spin vane until the salt is completely dissolved. From there, I'll be adding 330 microliters of 95% ethanol and 230 microliters of benzaldehyde. I'll start mixing those two phases together, and because ethanol is miscible with water, this allows benzaldehyde to interact with the thiamine, where otherwise benzaldehyde wouldn't be able to interact well with anything in the aqueous phase. Then I'll get some 3 molar sodium hydroxide, which will be used to activate the thiamine, and I'll be adding that dropwise just until the solution turns and remains a bright yellow color. So this is kind of what it'll look like once it's ready. And now I'll place it in the water bath and start heating that up Adding the air condenser and the thermometer to measure the temperature, and I want to keep it between 60 and 65 degrees, so right around here. But if it ever gets too hot, I'll just add some ice to the water bath to cool things down. Now I'll let everything react for about an hour, after which I'll get some of the solution out and spot a TLC plate with it, making sure to also spot that same TLC plate with a standard of the product. Methylene chloride will be used as the mobile phase to develop the TLC plate. Here we can see that the product is definitely forming, but there's still quite a bit of benzaldehyde, so I'm going to go ahead and add some more thiamine hydrochloride and let that continue to react. Once the 90 minutes have passed, I'll take the conical vial out of the hot water bath and remove the spin vane. And here you can already see some of the solid coming out of solution, but we'll let it stand there for a little while just to make sure that the product does crystallize out of solution really well. I'll even dip it in an ice bath to make sure that that process is complete. The product can then be moved over to the Hirsch funnel to separate it from the solvent. And I'll be rinsing it with some cold 50% ethanol. I want it cold so that the product doesn't also dissolve and go through the funnel. So I'll place it in some ice and then rinse the conical vial with that ethanol and the product that remains as well. After a few minutes, the product will be sufficiently dry to take out of the Hirsch funnel and then transfer over to a Craig tube to start the recrystallization process. I'll be using 95% ethanol as the recrystallization solvent, so I'll place that in the hot water bath and start adding it to the Craig tube to dissolve the product. Once it is completely dissolved, I'll transfer it to an ice bath to make sure that the solid product can come out of solution. Then I'll put it back into the hot water bath to redissolve the product. And finally leave it on a rack so that the product can recrystallize slowly at room temperature. I'll use a stopper and a propylene test tube to separate the crystals from the solvent, and I'll run it in the centrifuge for a couple of minutes. Now I can weigh out the crystals to calculate a percent yield, the empty watch glass being 9.736 grams and the full watch glass being 9.759 grams. I'll get the melting point range for the product now, starting a few degrees below 135, and it looks like this starts melting around 134.2 degrees and finishes around 135.2 degrees Celsius. Finally, I'll run an IR spec using the Nugel mold technique, and that turned out great. We can see a clear OH peak and then a carbonyl peak around 1678, plus some aromatic overtones, so that looks pretty good. Okay, I'm going to go over a few things on this NMR. If we look at the HNMR, we don't see any peak between 9 and 11 representing an aldehyde peak, so this is going to be the benzoin product. And I'm going to go ahead and label the molecule like this. This might look a little strange with the OMPs. They stand for ortho, meta, and para, and since the two rings are not equivalent, I'll label one of them as O', M', and P' to distinguish it from the other one. Please label your molecule the same way. This is just kind of how the key has it labeled, so it'll be easier for the TA's grading if everyone is consistent. There are a couple of helpful things on this NMR. The first one is just a zoom in of the peaks between 7.2 and 8 ppms. But the second one is a new kind of 2D NMR, which we haven't seen before, but it's going to be really helpful, so I'll be focusing on that. This 2D NMR is different from the one that we've seen before, which is called a het core, and it shows coupling between hydrogens and the carbons that they are directly bonded to. So on one axis we have the H NMR, and on the other axis we have the carbon NMR, and these spots show the coupling between the hydrogens and the carbons they're directly bonded to. This 2D NMR though is called a cozy, and it shows coupling between hydrogens to other hydrogens that are 3 to 4 bonds apart. So on each of the axes we have identical H NMRs, and these spots show coupling between those hydrogens. Since there are identical H NMRs coupled to each other, each hydrogen will see a spot for itself, plus any spots for other hydrogens that are 3 to 4 bonds away. For example, if we look at the doublet at 7.9 ppm, we can draw a line up to the first spot and then a line over to the left, and we see an identical doublet at 7.9, meaning that that's just the same hydrogen on the other NMR. But if we go up to the second spot and to the left, that signal is coming from the hydrogen that is 3 to 4 bonds away from the hydrogen that is creating the doublet signal at 7.9. So if we look at hydrogen O, for example, the only other hydrogen that it would see 3 to 4 bonds away would be hydrogen M. So we would expect to see 2 spots above its signal, one for itself and one for hydrogen M. Whereas if we look at hydrogen M, we'd expect to see 3 spots above its signal because it would see itself, and it also sees hydrogens O and P 3 to 4 bonds away. To use the cozy 2D NMR, we need some kind of reference point. So to get started, I'm actually going to look at the zoom in section first. And before I start analyzing any peaks, I'm going to recognize that the ketone is going to act as an electron withdrawing group for the aromatic ring on the right. So I can draw in the partial positives on the ortho and para positions. And then I'm going to start with the most de-shielded peak. It's a clear doublet with an integration that seems to be about twice as big as the smallest integration, so most likely 2, and it's the most de-shielded hydrogen, so this has to be hydrogen O with that partial positive there. Now from here, we could probably pretty easily move on to the next peak and analyze that one. It's a clear triplet with an integration that looks to be about half the size of the integration for hydrogen O, so it would be an integration of 1, plus it's the next most de-shielded hydrogen, so we could argue that that would be hydrogen P. But the 2D NMR takes away all argument or debate and can tell you exactly which hydrogens are which, so I'm going to show you how to use that. We've already labeled hydrogen O, so we'll use that as our reference point. And if we go up to the second spot above it, the hydrogen that is coupled to 3 to 4 bonds away would be hydrogen M. And since both axes are showing the identical H NMR, we can also label the triplet around 7.4 on the x-axis as M. Now we can look at the spots above the signal created by hydrogen M. The first one we already know is O, and the top one we already know is itself, hydrogen M, meaning that the middle spot would have to be for hydrogen P because that's the only other one that it sees 3 to 4 bonds away. As for the other peaks here, the 2D NMR is not going to be super helpful anymore because the peaks are too close and the spots start overlapping, so it's hard to distinguish what's going on there. The peaks are in the aromatic range, so we know that they're going to be for O', M', and P', but to figure them out, I'm going to look back at the zoom in. It looks like there are only 2 peaks left for the 3 hydrogens, so there's got to be overlap somewhere. And if we look at the bigger peak, it has a lot bigger of an integration, meaning that's where the overlap is going to be, so I'll come back to that. But if we look at the smaller peak, its integration seems to be about the same size as the integration for hydrogen P, which we know is an integration of 1, so that signal would have to be for P', meaning that the larger peak would have to be for both O' and M'. And that's all I'm going to go over. I'm going to leave the rest for you now, but there's a little introduction to a different kind of 2D NMR.